Hello and welcome to another session in physics. In this session, we will be looking at the topic equilibrium of forces. But before that, let us review the previous lesson. Welcome back. Well, at this point, let us try to define what we mean when we talk about equilibrium of forces. Well, a body is said to be in equilibrium if it is under the action of several forces, which makes it to accelerate uniformly or even rotate with uniform angular velocity, or even possibly remain at rest. For example, we talk about a stone at rest, we talk about the earth rotating round the sun. We also talk about a body moving along a path at uniform velocity. These kind of instances are instances that denote equilibrium of forces. As you can see from the diagram, that is an example of the earth orbiting or moving round the sun. At this point, let us talk about what we mean by moment of a force. The moment of a force, simply put, is the product of the force and the perpendicular distance. So force times perpendicular distance, F times d, gives us the moment about a force. And since the SI unit of force is Newton and that of distance is meter, that goes to say that the unit of moment is Newton meter, as you can see from the slide here. There are about two conditions that are necessary for equilibrium to take place. The first one is that the sum of the upward forces must be equal to the sum of the downward forces. The second one is that the sum of clockwise moments above a point must also be equal to the sum of anti-clockwise moments about the same point. And to expatiate more on this, we are simply talking about, let's say, F1 plus F2, which is equal to F3 plus F4. This is the instance of sum of clockwise moments being equivalent to the sum of anti-clockwise moments. We also have in bracket F1 plus F2 minus F3 plus F4. And when it is equal to 0, it means equilibrium has taken place. Also, we have clockwise moments, which is equal to F2 times F2x2 rather please, plus F4x4, and then the anti-clockwise moment, which is equal to F1x1 plus F3x3. That is weighted. And then we also have F1 in bracket, x1 bracket as well, plus F3 x3. We close the bracket, minus F2 x2 plus F4 x4. This is exactly how to take moments, about clockwise moments and anti-clockwise moments, and algebraically when you get all of them together, it gives you 0 to show you that the sum of clockwise moments is equal to sum of anti-clockwise moments. Yes, the sum of clockwise moments is equal to the sum of anti-clockwise moments. This is exactly what it looks like, to show us that at equilibrium the force is balanced. At this point, let us talk about a couple. A couple, put simply, is a system of two parallel but equal and opposite forces acting along the same line. Now, what a couple does basically is to get a body rotating. Its main function is to rotate a body. The moment of a couple, put simply, is the product of one of the forces and the perpendicular distance between the lines of action of the two forces put together. The distance between the two equal forces is what we call the arm of a couple. For instance, you look at a tap for instance, and then these are two ends of the tap. the distance between the two ends, point A and point B, is what we call the arm of the couple. And the moment of a couple is called torque. That is what we mean by the moment of a couple. At this point, let's look at the application of the effects of couples. The application of the effects of couples. The first application is that it is easier to turn a tap on or off by applying a couple. You look at this diagram very well. It is much more easier to turn a tap on or off when we have a couple. It is also very much easier to steer a car using the steering wheel. When you steer a car, it is very much easier to get it up and running when you use a couple. And then it is also much more easier to use a spanner using the effects of a couple to get to loose the bolts and nuts of a vehicle, just like you see in the second slide here. Instead of trying to use a single force with one arm, it is easier to use a couple with two of our hands, which makes the work easier and more efficient. Now let's take a look at this question here on the slide, and let's see how we can find the solution to that question. The question says that a uniform bar 15 meters long is balanced on a pivot placed at its midpoint. Now, a boy of mass 55 kg sits on one arm of the bar at a point 5 meters away from the pivot here. And we're asked what mass can be placed 2 meters away from the other end of the bar to keep the bar horizontally. I know it sounds like a lot of jargon, but let us try to represent it using a diagram first of all, and then when we do that, we can eventually find the answer to our question. So let's say this is our bar and this is the pivot on which the bar is resting. Now we're told that a boy of mass weighing 55 kg is sitting one end of here, so which automatically means that at this other side there is a mass kept at the other end 2 meters away to keep the bar balanced. So the distance between here and here is 2 meters. Now from the center of the pivot, automatically that gives us here the distance between here and here is 5.5 meters in the right level, 5.5 meters. And then at the other end here too, we have a line going to this point. This is 5 meters according to the question. And then you notice that from here, if we were to calculate everything from the end of the bar to the middle where the pivot is resting, it's going to give us a total of 7.5 meters, because the distance from here to here is 2.5 meters as well. Alright, so this is what the question looks like. For us to find the answer to this question, we're simply going to apply the fact that sum of anti-clockwise moments is equal to the sum of clockwise moments. Yes, sum of anti-clockwise moments is equal to the sum of clockwise moments. Now we want to take proportion, like taking proportions of the pivots, where M is the placed mass, where M is the placed mass. So we're going to have M times 5.5 equal to 55 times 5. That is the mass of the boy. So we're going to have, making M the subject of the formula, it's going to become 55 times 5 all over 5.5. That is, we're trying to make M the subject. So here we're going to have 275 over 5.5. This gives us 50 kg. That is what must be kept at the other end of the bar to keep it horizontally balanced. Okay, let's talk about center of gravity at this point. When we talk about center of gravity of a body, we're simply referring to the point through which the line of action of the weight of the body is always passing through, irrespective of the position of the body. It is the point at which the entire weight of a body appears to be concentrated. The center of mass of a body is the point at which the total mass of that body appears to be concentrated. So it's also the same thing as center of gravity. Center of gravity basically has to do with the point at which the Earth is using to pull that particular body down to its center. It is the point where all the force on that body is concentrated, and then it is also the point at which the entire weight of the body is also concentrated. Alright, so sometimes the center of mass may coincide with the center of gravity for some small objects, but not all times. They are two different things. Alright, let's talk about stability of objects. Now, when we talk about stability of objects, we are talking about how objects are in equilibrium. We have about 3 types of stability of objects, or 3 types of equilibrium. We have stable equilibrium, we have unstable equilibrium, and we have neutral equilibrium. When we talk about stable equilibrium, we are talking about the ability of a body to return to its original position when it is slightly displaced. This happens basically to objects that have a low center of gravity and a wide base. For instance, you're talking about a cone resting on its base, and then you're talking about a racing car with low center of gravity and a wide base, and then you're also talking about a ball or a sphere resting in the middle of a ball. Under unstable equilibrium, we are talking about a body that tends to move away further from its original position when it is slightly displaced. And that is where an egg comes into the picture. When you slightly displace an egg from its original position, it tends to move further away. We can also talk about a cone resting on its apex. These bodies that experience unstable equilibrium are known for their high center of gravity and a narrow base. Then, under neutral equilibrium, a body is said to be in neutral equilibrium if, when it is slightly displaced, it tends to come to rest in its new position. It means that at any point that body would come to rest. It does not favor one part or the other. This is found in cylinders or an egg that is resting on its side. Thank you so much for joining us in this lesson. To refresh your memory on what we've just discussed, please take the test that will appear on your screen.